This exhibition, which is called DTU, the Compute Rejseholdet, and Poul Hjorth from DTU Compute will open it. Thank you.
Good Monday, Moon. Can you hear me in the back? I love this opportunity to speak loudly in a library, which has also been forbidden. But so I get the chance to introduce this concept called the flying squad at DTU Compute. And so let me first remind you where you are. You are at the Technical University of Denmark, and I'm an associate professor at this department called DTU Compute, which has one of the nicest buildings around, I think. So, what does it look like when mathematicians do research? It doesn't look like much. Everyone knows that, right? That it's a very quiet affair, and even if you could break this guy's head open and look into it, it wouldn't be immediately interpretable. But everyone knows that, that mathematics is an essential part of science and technology. It is not in itself a natural science, but it is a branch of philosophy which is completely necessary for all modern practice of natural science and technology. But there is another aspect to it. So if we carefully read this picture again from the right to the left, there's a point that mathematics can actually emerge out of practical problems. In fact, I would go as far as to say that almost all mathematics at some point or another has emerged from practical situations. And so there is a kind of causal loop that makes mathematics arise out of practical problems and then in turn give assistance to technological problems. But I cannot stress enough that basic research in mathematics is the foundation of what we do. So there's a reason why we have basic research in mathematics going on at this university. But given that, the so-called flying squad concept is a relatively new concept, which is based on an older concept of more stationary study groups, and it simply permits enthusiastic individuals to leave the ivory tower and go out and use their mathematics in real life. So ideally, a company who is stuck with some mathematical problem will contact DTU, and then DTU will send out their flying squad. Now, of course, if you see the exhibition back there, the exhibition itself is strongly inspired by police work and CSI movies and everything exciting. When it comes to that, the DTU Flying Squad consists also of these individuals, but actually in principle of most of the researchers at DTU Compute, which count all in all several hundred people. So this is just an example of people, and probably the flying squad will be different from task to task. Each problem requires, by its nature, a specialized team of mathematicians. And once they get to work, we are back to the thinker again, because in contrast, I guess, to the work of criminal agencies, the work of mathematicians look on the surface of it not so amusing, except for those who actually practice it. I can assure you it's a lot of fun. So we think that it is a win-win concept, both for companies who participate and for the academics. So the companies who have a mathematical problem or mathematical issue get these problems you could call flash-fried. Here's another metaphor that we are cooks. They get their problems very quickly treated by independent academic experts. And of course, out of this, you will get contacts and possible exchange of students and potential recruits to the company. The academics get to test their skill on real-world problems. And this is crucial for any development in mathematics. If you think that it has a practical relevance, then you should also sometimes go out and prove that it does. And several times we bring back from industry contexts, as I said, new ideas for basic mathematical research. And I can say for myself that one or two or more exam problems have arisen out of industry contact. So this is a very nice situation. Let me give you, in the remaining time here and before you fall asleep, a few examples of the tasks that we have covered. Now, the flying squad is not an old concept. It is not that many weeks old. And so we don't have a large repository of specifically flying squad tasks. But as I said, the flying squad has grown out of an older activity, an activity that stems back actually to 1968. There was mathematics in 1968, I can assure you. And this is the so-called study groups with industry that originated in Oxford, and since 1998 has been practiced here in Denmark, an annual meeting, a more stationary activity where mathematicians engage with companies over a longer period, a full week or so, to do the same kind of mathematical problem solving. So some of these examples will be from these study groups, but the first one of the 5 examples that I will show you is actually a flying squad problem. So this had to do with particle sizes in tap water. You hate to think that there are particles in your tap water, but there is. And some of these particles are just tiny bits of rock that doesn't do all that much damage. Sometimes these particles are bacteria, and then it's not so nice. Tap water is regularly monitored for bacteria, but we would like this monitoring to be almost continuous, because sometimes it happens that people start getting sick before the waterworks really know what's going on. So we were contacted by a very small company who uses laser scattering. Actually, in a slightly different context, they supply these types of equipment to the brewing industry, and there's a concept called turbidicity, which is translated more or less to murkiness. If you are brewing and you have a yeast-filled liquid, you want to compare the murkiness of various liquids, and this can be quantified by using Mie scattering. But this company was interested in if we can detect yeast cells in a brewing process, why can't we detect bacteria in drinking water? So they had some initial studies, but they weren't too hard on theory, and they put a series of questions to us. Mathematicians like specific questions, And initially they needed to know how true is this, and we could assure them that it's a long-established theory in scattering processes that yes, you have a dependence, but on this graph here, where you have particle diameter out of this axis and this scattering ratio on the other axis, you see it's a fairly complicated function, and it's not a one-to-one relationship unless you restrict yourself to segments of the curve. So you have to know exactly where you are with respect to particle diameter. So horrible mathematics, which we will bypass very quickly. And then they had a curious observation, which we could clarify for them, because a part of this curve where they actually are operating passes almost through the point 1.1. And so this is simply a mathematical coincidence, and it's not a miracle that, that this happens. But it's nice to know. And finally, they wanted to know, could we suggest to them an even better measuring technique? And yes, we could, because if one uses polarized light, then you get a much bigger range of particle sizes to detect. And this range actually includes some of the hazardous bacteria. So as far as I know, they're busily changing their equipment now. I don't know if they're putting sunglasses in front of it or whatever into polarized light so that they can offer it to the Danish waterworks to check for bacteria. So hurrying on, here's a famous example about how you detect the wear and tear of paved roads. You may think that just looking and counting potholes in the paved roads would be enough. But actually, long before the potholes set in, the paved roads showed sign of a very subtle kind of wear, which you can detect by pressing down on it and watching the bulge or the deflection as a function of the weight that you put on it. It's almost like, I don't know, caramel or some other thick substance which has a braking that sets in after sufficiently many cars have driven on the paved roads. So the Danish road authorities constantly monitor our roads by walking out and pressing down on them. And this can be a lengthy and dangerous affair for the people who do it if it wasn't for this company who have found a way to put the measuring device on wheels. Very cool concept where they use laser lights. So they have inside the truck, they have double shift lasers who measure the velocity of the deflection as the car rolls across the track. But the company needed a simple mathematical model to quantify their measurements, and so they were very eager to see if you could cook up a simple mechanical model with enough mathematics to be flexible, but not too much mathematics, so it became impossible. And we could. I won't go into details, but you can also imagine almost like a mattress on your bed. This is a very crude two-parameter model of a road that combines an elastic underside with a Young's modulus with a beam theory, and you get a fourth-order differential equation. Lovely to see. And the company was very happy, and it modeled their data in a very nice way, and they have since sold a number of these trucks, and we are very popular. Every time we come by, they wave to us. And so mathematics has a good name with this company. So a famous patent on pumps goes back to the early parts of the previous century. And if I just show you the patent drawing, I would imagine that you would be a little bit perplexed. How is this a pump? Well, a famous Danish company came to us with this patent and said, can you explain mathematically what's going on here and help us come up with similar designs and alternate designs that uses this patent. Fortunately, at DTU, we have some excellent geometers. So here's the idea of in a more transparent way. So the pumps are like the Archimedes screws. So something is going around and it's sucking up fluid from below and squeezing the fluid through a series of chambers up to the top. So it is not a compressor, it is actually a pump because it works with incompressible fluids. So you see the purple color is liquid, which is taken in and then squashed up through the pump. And inside the pump is a rotating shaft which lets fluid in and then traps it and pushes it further up the construction. The mathematics is, if you take a circle and inside of it is a smaller circle which can roll and is of half the diameter, you will notice that a point on the inner circle will trace out a diameter on the larger circle. And if you fatten up this construction, you will get a little mechanical system like this. And if you take this image and stack them at various stages of the rotation, you get this picture. You recognize this, and then you stack it and twist it and stack it and twist it some more. And this is actually the construction. If you now connect all the red circles, voila, there you have, by DTU mathematics, the basic construction. And once you understand how this works and you can code this into MATLAB or Mabel, you can start playing with other ideas. If you take the entire construction and roll it inside an even bigger circle, now you get that the diameter takes 3 times to pass around. So you can get all kinds of integer relations here. If you continue the construction, you get a sort of a Wankel engine-like version of the pump, which is also complex. And all of these pumps, as soon as you have a mathematical description, you can quantify it and you can ask about the efficiency and the pumping rate and all that. So with this work, the company was able to study the types of pumps that they needed, and they were very happy. So my next to final example is one of our favorite examples, and I bring it in just to show you the diversity of problems that will be presented to mathematicians who engage with the outside world. And this was a problem in the UK from a zoo which came to us and said, we need more penguins. And instead of going to South Africa, this is actually the South African penguin. It lives on the continent of Africa. What they do is they take the eggs from the penguins. So the penguin sometimes lay eggs, and they sit on the eggs. And if you take the eggs and put them into a hatching device, originally conceived for chicken eggs, you can get chicken penguins. But the problem from the company was that this was not as effective as they thought it would be. Not that many of the eggs actually hatched, and they wanted to know, are we doing something wrong with the setting of the hatching machine? So what's so different between a penguin egg and a chicken egg? So they can tell from the penguins, when they look at them and count, they can tell that the penguins are actually turning their eggs at a rate of about once every 10 minutes or so. So this is the key to what makes penguin eggs different from chicken eggs. So, and they wanted to know, could we make a stab at what is so different with the turning of the eggs, and why are they turning the eggs? And so the first thing we drew was a big circle on the blackboard. And inside the circle, you see various elements of the egg. Simplified, of course, there's the embryo and the egg white and the yolk. And this is all we need to study. And so in the course of this, we had a long brainstorm where we first came up with some wrong ideas. So you would think when you are hatching something, you put some warmth on it, and especially in the Antarctic, things are very cold, so maybe it has to do with the fact that it needs to keep the top of the egg warm, and it's turning it like you are baking something constantly. But it turns out the thermal diffusion time scale is very long, and so you can see on the order of an hour. So what the penguin does not have much to do with the thermal diffusion time scale. You could think, is it a buoyancy issue that the egg yolk, for some reason, needs to be on top or at the bottom, and this is why the penguin is turning its egg. But then you can calculate that also fairly easily from constants, and it turns out that this rise to the top takes place in just a few seconds. And so there's no point for the penguin in waiting 10 minutes before it turns it again, if this was the critical issue. So finally, we thought about rotation. So could it have something to do with this triple structure, that you want to rotate the egg? So what are the forces involved? Well, there's a torque, there's a buoyancy torque, and there's a viscous torque, and when they compete, you get a time scale of about 10 minutes. So we thought this was probably it. So, but why is this it? Well, so we think that when the situation is like this, the embryo is growing, and it very quickly depletes a near zone from nutrients, and maybe even emits some leftovers. So in order to give it access to new nutrients, you simply turn the egg, and then the depleted zone gets smeared out, and now the embryo has access to fresh egg white and can grow again until after about 10 minutes, then you turn it one more time, and maybe it ends up over here, and you are repeating the process and constantly giving fresh egg yolk. So we suggested this to the zoo, and they implemented it in their hatching program, and they got lots of chicken. They got lots of chicken. And so in this sense, the mathematicians became the grandfathers of a whole generation of African penguins, which is now not considered an endangered species. So my final thing here is actually a slightly work in progress, but I bring it in just to show you the range of mathematical ideas that can be used. So in high voltage circuits, sometimes you get a spark, and sometimes if the spark is violent enough, it will set everything on fire. And so you need to have a mechanism that kills the breakthrough almost before it happens. So if you have a spark, you can have an optical sensor which at the speed of light detects the spark and then immediately cuts the circuit, so that this happens on on extremely fast timescales, so you can cut your circuit and prevent a fire. So, but the question the company needed to know is, if you have a complex circuit structure, where should you place these optical sensors, which are not cheap? You could say, let's place them everywhere, but this makes the thing impractically expensive. So how little can you get away with? Well, the answer comes from graph theory. Because there's a famous problem in graph theory called the Custodian Problem, which is essentially the same problem, is where in a museum should you place custodes so that they can keep an eye on all of the walls. And the solution is to triangulate your area and then color it because every one of the colors can now act as a supervisor, as a custodian or an optical switch. And so the number of nodes in your triangulation divided by 3 will easily serve as a bound on the number of optical sensors. And so here's a solution to the circuit that I had. So that was the final one of the 5 problems. How do you get, I know many of you are not companies, how do you get the flying squad to visit your company? Well, you can contact various people, either Jakob Ferdinand, this will all be on the website and placed in the exhibition also, or Mark Ries, who's sitting down in the corner, Mark, or yours truly, with also contact information. So we cannot do this constantly because we also do teaching and research, and I have some teaching to do in not so long. But I hope I have given you a small taste of what the flying squad does and how we solve problems. So thank you.
Yes, we just want to thank Poul Hjorth. It was a nice talk and a very exciting talk. And I think it's especially important that you know that you can always get in contact with him. You can send him a mail. And if you have a company, it's not that unusual that young people have their own companies. You are most welcome to take contact to Poul. Thank you very much.
Thank you.